Good morning, everybody. Today we will continue with X-ray magnetic circular dichroism. This is also one of the important applications of X-rays. So let me start with the advantages of the X-ray magnetic circular dichroism. First of all, like XRMS, it is also element specific because these experiments are carried out in synchrotron radiation sources. So we have monochromators in the beam lines. So depending on the element, depending on the material under investigation, you can select specific energy range, okay? So this method is also element specific. So if you have a thin film, or let's say double layer on silicon, let's say this is iron, nickel, and this is cobalt, let's say, and here you have platinum. The thickness of platinum, let's say 1 nanometer, and thickness of cobalt is 1 nanometer, and thickness of this iron nickel is, let's say, 5 nanometer. So by using this method, you can investigate cobalt, iron, and nickel separately. So for this layer, you can get information by using both iron L2, L3 energies and nickel L2, L3 energies. In addition to that, if this platinum becomes ferromagnetic due to the neighboring cobalt, you can also see that effect within the platinum. So this is very nice method, but it is important to remind you that it is surface sensitive method. So we can get information from the surface just about 5 nanometer, let's say. So I will explain why it is surface sensitive. So what about other advantages of this method? We can determine spin and orbital magnetic moments of the elements and materials and the layers separately. This is also a very unique feature in XMCD, and we measure XMCD signals by changing the polarization. During the last lecture, we have seen XRMS, X-ray resonant magnetic scattering, and during the last lecture, we have seen what is the importance of the polarization. So for the experiments, the type of the polarization is very important. And here also in XMCD signals, we can measure the signals by changing the photon polarization. We will talk about this. And compared to the XRMS experiments, we cannot apply magnetic field to the sample during the measurement. So remember the XRMS experiments from the last lecture. You can apply magnetic field, but during that type of measurement, we cannot apply magnetic field because measurements are affected from the magnetic fields. This is related to the XMCD setup. I will also talk about this one. And I can say that compared to the XRMS experiments are harder, let's say. So it is not so easy to get good signals, especially from some special samples. So sometimes special sample preparation conditions are also required in XMCD measurements. So what about the setup? Actually, there are many different XMCD measurement setups. Here you see a Alice diffractometer, which I have shown you during the last lecture for the XRMS experiments. So this is the ALICE diffractometer at BASI. We have synchrotron light source here. Okay, this is the undulator, this is the beamline, and this is the end station, ALICE diffractometer. So this is the beamline, X-ray beam comes, and this is the sample. And here we have detector. We have magnetic field source. This is important for XRMS experiments. So we have vacuum conditions here. We can change the temperature of the material. Okay, this was the XRMS chamber. We have discussed all the details of the experimental setup during the last lecture. For this reason, I will not go into detail today. So now let's discuss what is XMCD and what is the reason for such behavior in magnetic materials. So during the last lecture, we have seen that XRMS signal looks like this. You can find this type of XRMS signals in the transparencies of the last lecture. So during the last lecture, I have told you that I will also explain the behavior of this shape, the intensity as a function of photon energy, why we have this type of behavior. We did not discuss this one during the last lecture. And today, you will see the reason to observe, to obtain such signals from XRMS and XMCD signals. Actually, the origin is more or less the same. Both of them are absorption experiments, okay? And they can be converted to each other. So you can convert XMCD signals to the XRMS signals by using optical theorem and Kramer's chronic relations. And you can also convert XRMS experiments to the XMCD results. We can say like this. So what about the reason to observe such signals? In order to explain this one, we can use two-step model, which is explained in that literature and also in that paper, okay? I can strongly suggest you to read the details within that papers and book chapter. So here I will shortly summarize. Here you see that the band structure of ferromagnetic materials. What we have here, this is the 2p1/2 level, let's say L2 level, and here we have 2p3/2 level. The other name is L3 level, okay? And here we have 3D level. In case of non-magnetic materials, for example, copper, the 3D level is completely filled with electrons. We have 5 spin-up electrons and 5 spin-down electrons in the 3D level. So all of the levels are occupied, right? But in case of magnetic materials, like iron, like cobalt, like nickel, we have unoccupied 3D levels. We have unpaired electrons in the 3D level. So we have empty states, okay? You can consider like this. So if we use X-rays, let's consider we have a material here, okay? It is thin film. And then we send an X-ray to the material. So what happens if I send that X-ray to the material? So if the incoming X-ray energy is close to the binding energies of that electrons in that energy levels, you can excite them, okay? You can produce photoelectrons, you can produce Auger electrons, you can produce fluorescence X-rays, okay? General absorption mechanisms are formed if you have X-ray energies close to the binding energies of dead levels. So you remember that information from the X-ray matter interaction. I will not go into detail. So let's consider that we have sent X-ray, soft X-ray, to the material with the energy of the L3H, okay? Then you excite spin up electrons from that level to that level. Or you can excite spin down electrons from that level to that level, okay? But what about the unoccupied 3D levels in that condition? So in the first step, you excite electrons, and in the second step, you are looking if there are any empty states for the excited electrons. So this is called as two-step model. The first step, you excite electrons, spin up or spin down electrons from that levels, and then here we have 3D bands which can be viewed as spin sensitive detectors, okay? So in case of non-magnetic materials, the number of spin up and spin down electrons in the 3D level are same. So all of the 3D levels are occupied and all electrons are paired, we can say, okay, in the 3D level. So nothing will be different if you use right circularly polarized light or left circularly polarized light to excite electrons from that levels to the 3D level. But in case of magnetic materials, the situation is completely different. Now let's try to analyze it. Okay, it is very simple. Just try to stay on the line. So let's consider that the energy, incoming energy of the X-rays is around the L3H, okay? We have adjusted the energy to this L3H, let's say, okay? And then we are using right circularly polarized light. We have discussed the polarization during the last lecture, okay? I will not go into detail. So we are using RCP. So if you send RCP to that level, I mean you send photon with that energy with the RCP polarization, okay, then you can excite 62.5% this spin down electrons to the 3D level, and you can excite 37.5% spin up electrons. For the spin up electrons, we don't have enough place here. But for the spin down ones, we have enough place because there are unoccupied 3D levels, okay, for the spin down electrons. And if I use RCP, I mostly excite spin down electrons. If I use LCP and send X-ray with that energy, then we mostly excite spin up electrons. So it is vice versa, you see? So now look at this one. The blue one shows us RCP. The red curve here shows us LCP. For RCP, blue one, we mostly excite spin down electrons, 62.5% spin down electrons, and here we have enough place for them, okay? Then we have higher signal here, and for the LCP photons, we mostly excite spin up electrons and less spin down electrons. Less spin down electrons. For the RCP, we have excited 62%, let's say, spin down electrons. For the LCP, we excite 37% spin down electrons. Okay, so there's a difference for the same energy, for the same element, for this reason. Let's go to the L2 edge. You set the incoming X-ray energy to the L2 edge, binding energies of electrons at that level. So if you use RCP, blue one, we can excite 25% spin down electrons. Here you see. But if you use LCP photon to the L2 energy, we can excite 75% spin down electrons. Okay. For the L2 energy level, we can excite for the RCP 25% spin down, and we have enough place for them. And for the LCP, for the red one, we can excite 75% spin down electrons. Okay, then you have difference. This difference occurs if you have empty states in the 3D level. If you have unoccupied 3D levels in the 3D level, let's say. So if the 3D level is completely filled, if there is no unoccupied states, then these two curves, blue one and red one, will be same, and there will be no difference which occurs in non-magnetic materials. But if the material is ferromagnetic, like iron, cobalt, or nickel, then we have unoccupied 3D levels. Then for the RCP and LCP, we see different curves as a function of energy in the XMCD signal. This mechanism is called as two-step model. The first step is the excitation of the electrons. The second step, you can consider that the detection of the electrons. Do you have any question here in that part? Okay, then let me continue. So we have three different measurement setups or mechanisms in order to carry out XMCD experiments. This is total electron yield method, in Turkish toplam elektron ürünü. Remember that XMCD experiments are absorption experiments. So we have absorption products, right? We send X-ray, soft X-ray to the material, and then we produce photoelectrons or J electrons and also fluorescence X-rays. We have discussed all these things in X-ray matter interaction subsection. So you can see details in that chapter. So synchrotron radiation comes and photoelectrons or J electrons and fluorescence X-rays are produced, okay? So if you make a contact on top of the surface, just put a contact on the surface. So you can measure the current via the photoelectrons and or J electrons produced within the material, okay? So the number of photoelectrons and or J electrons, thus the magnitude of the current changes as a function of energy. If the incoming photon energy is around absorption edges, then the current will increase because at that energies we will produce more photoelectrons, more or J electrons at that energies, and then the current here, total electron yield, will increase and also will increase here, okay? because incoming photon energy is around the binding energy of the electrons for that material in that energy range. So this is the total electron yield. So what about the thickness? We can get information for this type of measurements. We can get information from 5 nanometer, let's say, from the surface. Okay, you cannot get information from deep because the photoelectrons or Auger electrons, which are produced in deeper levels of the sample, cannot go out because they lose their energies, okay, until they reach to the surface. So we are taking the data from the surface. We collect the electrons from the surface and then we measure the current, right? So if the photoelectrons and Auger electrons are produced via synchrotron radiation in the deep of the material, they cannot go to the surface and we cannot measure them. For this reason, this method is surface sensitive and we can collect information from, let's say, 5 nanometer from the surface. Okay, so what about the result? Result is similar, which I have discussed here. Let's say you use right circularly polarized light and you are measuring a ferromagnetic material, iron, for example, in that case. So you scan the energy and you collect the total electron yield, okay? Total electron yield means that total number of photoelectrons and Auger electrons produced within that material. And then around the absorption edges, you have that intensities, that T result, and around that absorption energy, we have that result. So depending on the right circularly polarized light and left circularly polarized light, we have different XMCD signals if the material is ferromagnetic or magnetic, you can say. So the next method in XMCD experiments is called as Fluorescence Shield. As I told you, in the absorption experiments, we have 3 main products: photoelectrons, Auger electrons, and fluorescence X-rays. Okay, in that method, we measure fluorescence X-rays. So you send X-ray, soft X-ray to the material, photoelectrons, Auger electrons, and fluorescence X-rays are produced. But I'm not dealing with electrons within that type of measurement. I just deal with the fluorescence X-rays leave from the sample. So here we have a fluorescence detector, which is waiting for the coming fluorescence X-rays from the sample, okay? And as a function of the energy, if you repeat the measurement again, you can get this type of signal. Here we have intensity, number of the fluorescence X-rays coming to the detector. So here, let me tell you something else. At the beginning of my lecture, I have told you that during that type of measurement, we cannot apply magnetic field, okay? Why? Let me explain. In that method, here we have photoelectrons and Auger electrons on the surface, okay? They are produced during the absorption mechanism, and we are measuring the current. If you apply magnetic field in that direction or in opposite direction, so there will be force, magnetic force, acting on the charged particles, electrons. Then their trajectories will be deflected due to the magnetic field, and your result will be affected. So for this reason, we do not apply magnetic field during the measurement. If it is required, you can do like this. First of all, apply magnetic field and magnetize your material, and then remove the magnetic field during the measurement. So there is no magnetic field. Changing the polarization right circularly polarized light, left circularly polarized light, you can carry out energy scans. Now let me continue with the fluorescence yield. What about the magnetic field? In case of this type of XMCD experiments, of course, we know that fluorescence X-rays, photons, are not affected by magnetic fields, right? So you can consider that you can apply magnetic field during that measurements. Indeed, this type of measurements preferred for such property of the fluorescence X-rays. They are not affected from the magnetic field. So you can apply magnetic field, but you must be very careful that here you have a fluorescence detector, okay? And fluorescence detector is usually very close to the surface of the material. Then if you have a magnetic field source here, your detector can be affected from the magnetic field. Just remember the detector working principles. Most of the detectors convert photons, X-rays, to the electrons, right? In order to produce a current, which is proportional to the number of the photons come to the detector. So since we have current within the detector, it can also be affected due to the external magnetic field you applied during that type of measurements, okay? So it is also better to use magnetic field if it is required before the experiments, and during the experiment, don't use magnetic field. So it is not advised. So the result is more or less same. We have already discussed. So for the same material, let's say this material is same, and you measured this material by using TAY method, and you get this result. And by using the fluorescence yield method, you should get more or less the same result, okay? And the behavior of the signal and also absorption energies must be same if you are talking about the same sample and same energy range. Is it clear?
Yes, but in my slides, you draw in fluorescence yield TEY current measurements here.
Okay. Okay. It is.
But you don't have in your slides.
I see your point. Actually, in that transparency, I had collected all possible XMCD experiments in a single figure. I can show you like this. But it is confusing. For this reason, I have removed that one. So here, this sample, this is the incoming X-ray. So if you measure the scattered photon, then this is XRMS. Okay, we have done it during the last lecture. So if you measure photoelectrons from the surface, if you measure the current, then this is TAY method. And here we have fluorescence X-rays. If you measure them by using a detector, this is fluorescence yield, okay? And we have another method, which is transmission. You send X-ray like this, and then you measure the final intensity here. And this is transmission method. Within the previous lecture notes, I have collected all of them in a single graph. For this reason, maybe you have confused.
How about you draw that some fluorescence X-rays get off the material from a different direction, so the detector is turning around the material, or the lucky ones which are reach the detector. So we
good question. Good question. Actually, the fluorescence signals are produced within the material can go everywhere, okay? But detector is waiting at certain position very close to the surface. Of course, I cannot measure, I cannot detect all fluorescence X-rays which are also going in other directions. I have only possibility to detect X-rays produced in that direction. Is it clear?
Yes, thanks.
Okay, never mind. Then let me continue with the transmission method. This is the last method. One is total electron yield. We measure photoelectrons and Auger electrons. And the second one is fluorescence yield. And the last one is transmission. The third method, third XMCD method. So we have incoming photon intensity here, and then this is the transmitted photon intensity, and it depends on the I0, and it depends on the mu, it depends on the thickness of the material. We have discussed this one during the X-ray matter interaction. I will not go into detail, okay? But the important thing is that let's consider here at the beginning, you have many photons, and whenever they enter into the material, they will be absorbed, okay? But this absorption will be maximum around the L3 and L2 edges, okay? If you scan the energy around the absorption energies of the material element within that sample, so around L3 and L2 energies, the absorption will be maximum and the incoming photons will be absorbed. They will be converted to the photoelectrons, fluorescence X-rays, and also Auger electrons, okay? Then the transmitted number of photons will be less than the incoming number of photons, okay? And this absorption will be maximum around the L3 and L2 edges. So transmission measurement or transmission data in XMCD measurements looks like this. So what is the tricky thing here in that type of measurement is that the sample preparation is not so easy. You have to prepare very thin samples in order to allow soft X-rays to transmit through the sample, okay? So the sample preparation procedures are not so easy during that measurements. I mean, you can use chemical methods or you can use other, let's say, expensive methods like focused ion beam method, okay? But this one, fluorescence yield and total electron yield, much easier, okay? You don't need to do something else to prepare your sample. Just gross your material and put into the vacuum chamber and you can carry out your experiment. This is also the same for the fluorescence yield compared to the transmission, let's say. Do you have any question here? Okay, then let me continue with the measurement conditions. How to carry out XMCD experiments. Do you need to do something else before the experiments? Yes, we have discussed sample preparation and system preparations before the experiments. We have discussed all these things during the XRMS lecture. So as I told you, we were using the same Alice diffractometer for the XMCD experiments. So this diffractometer allows us to carry out sample alignment, okay? But in many XMCD measurement setup, diffractometer is missing, okay? It is not required actually, okay? So if your system is pre-aligned for XMCD experiments, then you don't need to carry out sample alignment. But in case of that chamber in ALICE diffractometer, we have that opportunity. You can align your sample. And as we discussed during the last lecture in XRMS, you can prepare, you can select the best incoming photon angle, okay, the best theta angle, theta to theta angle. You can, actually 2 theta is not required here. So you can select the best theta angle, incoming photon angle, and then you have to set the temperature. This is very important. Temperature shouldn't fluctuate, otherwise you cannot get good data. Polarization is selected, and then we scan the energy range depending on the material under investigation. So we change the polarization, scan the same energy range again, okay? Like this one. Select the polarization. Let's say blue one is taken for the right circularly polarized light. Scan that energy range for that material, and then change the polarization for the left circularly polarized light, then scan the same energy range. This is the general procedure. So what about the electron binding energies? As we have discussed in XRMS lecture, we have different binding energies for the iron, for the cobalt, for the nickel. Actually, for all elements in periodic table, we have different binding energies. For example, for the iron, we have electron binding energies around 706 electron volt around L3H, but around L2H, we have around 720 electron volt. And this energies changes for cobalt to 778 electron volts, 793 electron volt. For the nickel, we have different energies. Okay, for manganese, we have different energies. For chromium, vanadium, we have different energies. We have discussed this one during the last lecture. So this electron binding energies can be found in that X-ray data booklet published by Lawrence Berkeley National Laboratory. You can find a free version of the PDF of that X-ray data booklet. So now you have synchrotron light source, and you have undulator, monochromator here. There is an end station. Your experimental setup is located here. And monochromator is very important because you can change the incoming photon energy, and then you record the intensity in terms of T or in terms of intensity. Okay, so depending on the element under investigation, you can get signals in different energy ranges. So here you can see iron, here you can see cobalt, here you can see nickel. Look at the iron between 700 and let's say 730. You can see absorption edges. Look at the iron, 700, between 700 and 730. You can see that absorption energies. And for the cobalt, between 778, 790, is in that range. Okay, 778, 793, you can see that energies. So it is element specific. You scan the whole energy range depending on the limits of your beam line, okay? Then element specifically, you can measure your sample. This is very nice property of the XMCD measurements. So how to analyze XMCD results? So what I have told you that at the beginning of my lecture, I have told you that by using that method, by using XMCD method, we can determine spin and orbital magnetic moments of the elements within the sample separately, okay? So let's consider you are analyzing the iron within that sample, and you can get the spin magnetic moment and orbital magnetic moment of the iron, okay? And you can measure, you can calculate the contributions to the magnetism separately. This is very nice property of the XMCD. And how to do that? This can be done by using the sum rules, okay? They are summarized and explained in that paper. You can find that. So here we have S subscript Z, L subscript Z. This shows spin magnetic moment. This shows the orbital magnetic moment. And how to calculate them? Look at this one. Let's consider that you are measuring the iron, okay? And you use right circularly polarized light, blue one, and then scan that energy range, and you change the polarization to the left circularly polarized light, and then you can you scan the same energy range again, okay? So what we have discussed what we have discussed during the last lecture in XRMS, you can plot that two signals as asymmetry ratio, okay? Do you remember the asymmetry ratio we have discussed in XRMS experiments? So here we have two measurements, blue one and red one, okay? Let's consider that this blue one is I plus and the red one is I minus. What is the meaning? You use RCP and measure that intensity, I plus. You use LCP and you measure that intensity, I minus, okay? If you take I plus plus I minus divided by 2, then you get X-ray absorption spectroscopy signal, XAS signal, okay? Like this. So you use both of them within that equation, and you have that signal. The name of this signal is called as, or the name of this data is called as XAS, X-ray absorption spectroscopy, okay? But if you plot that two intensities in asymmetry ratio, which we have discussed during the last lecture, I minus minus I plus over the sum of them, okay? This is the asymmetry ratio. This gives us the XMCD signal, X-ray Magnetic Circular Dichroism signal. And here we have this behavior, asymmetry ratio, let's say. So if we integrate that curve, we have, let's say, this area under this curve. The area is called as C. And here we have the area in the negative side called as A. And on the positive side, we have B, you see? By using that C, A, and B, I can calculate spin magnetic moment and orbital magnetic moment separately for that element, okay? This is given by some rules. So what we have here, if you would like to calculate spin magnetic moment, we have that equation, minus 2 A minus 2B over C. You see, here we have times 10 minus N3D times Bohr magneton. You know Bohr magneton, but here we have N3D. What is this one? This is number of electrons in 3D level. Number of electrons in 3D level. Just consider iron, cobalt, nickel, and copper in periodic table. Okay, for the iron we have 26 electrons, and 6 electrons in the 3D level. Okay, so 3D 6. For the cobalt, we have 3D 7. For the nickel, we have 3D 8. And for the copper, we have 3D 10. Okay. In case of copper, just put 10 here, 10 electrons in the 3D level. The orbital magnetic moment and spin magnetic moment will be 0 for the copper. Indeed, copper is not magnetic. Since we have unoccupied levels in the 3D level of the nickel and cobalt and iron, they are magnetic. They are ferromagnetic. They show magnetic signal. Okay, so they show magnetic behavior. So for the iron, just put 6 here. For the cobalt, just put 7 here. For the nickel, you can put 8 here. Also same for this case. Okay. So this is how we calculate the spin and orbital magnetic moments. But what do you see here? We have negative number. Actually, the area is here negative. Here we have positive. If you multiply with negative number, this will also be negative. Negative 1 here. And if you multiply negative number with negative number, then finally it will be positive. Okay. It is also same. This part is same for the orbital magnetic moment. But instead of this one, we have this equation here, -4/3 A plus B over C. Okay, the area here usually is bigger than the B, then here we will have negative number. C is positive, negative number, positive number. Here we will have negative number, and here we have another negative. Finally, we will have again positive. Okay, so by using the sum rules, you can calculate spin magnetic moment and orbital magnetic moment of each element under investigation by using XMCD measurements. Do you have any question here? Okay, for the details, you can visit that literature. So now let me finish with that transparency. Here I will show you one X-ray absorption spectroscopy XAS result. So I have already explained what is XAS. You carry out 2 experiments with different polarizations, and then you plot that measurements in that form, I plus plus I minus divided by 2. Okay, this is the XAS signal. Here I have XAS signal for the cobalt element within that material. In the previous lectures in X-ray diffraction in XRMS, we have discussed that material. Okay, so I would like to investigate magnetic behavior of cobalt within that material. So then I have to scan energy range for the cobalt. Look at the cobalt. 778 for the L3 and 793 for the L2. So I should scan that energy range. Okay, look at this one. I have started from 775, and here we have L3H, and here we have L2H, and I finish around 800 electron volt. So this energy range I scanned, and I have used RCP photons and LCP photons. I have recorded 2 signals and then plot that one in XAS. Okay, so then I have such signal. So what this signal tells us? Before going into detail, I would like to tell you that which method had been used during that measurement. So in order to carry out that experiment, I can use TAY method, I can use fluorescence method, I can use transmission method. So during that measurements, in order to record that signal and that signal, we have used TAY method, total electron yield method. So you send X-ray to the material, and then photoelectrons and Auger electrons are produced everywhere. And I put a contact on the surface, and then I measure the current. Okay, this is total electron yield on the left side. So what you see here, actually, if the cobalt here is metallic, I mean, it is not sitting on the lattice of the zinc oxide. If the cobalt is alone, then you should see sharp peak around this L3H. I can show you here. This is another data from that reference. Okay, what do you see here? We have cobalt metal. It means that pure metallic cobalt. We have this signal. You see, very sharp peak, let's say, compared to the other signals. And if you measure the cobalt oxide, oxidized cobalt, here, another measurement, cobalt oxide. Okay, what do you see here? This black curve. You see many features around L3H of the cobalt. Okay, if the cobalt is oxidized, if the cobalt makes bonding with oxygen, you see many structure here. This is also called as multiplet structure. So, but if you are measuring the pure cobalt, metallic cobalt, it is more or less sharp peak. Okay. So then by using that property, I can understand that whether this cobalt is metallic or this cobalt makes bonding with oxygen and sits on the zinc oxide lattice. I can see that by using that measurement. So then we have carried out energy scan for both polarizations, RCP and LCP photons. Then I have plotted XAS. What do you see here? I have features around L3H. So the data behaves like cobalt oxide. This indicates that this cobalt sits on the zinc oxide lattice within that material and then makes bonding with oxygen. So we see fine structure around L3H due to the cobalt oxygen bonding. So this method is also very useful. So this XMCD measurements can give you information about the magnetic properties of the material. In addition to that, you can use that results to understand the structural properties and position of the elements within the material. Do you have any question with that part? With that one, I would like to finish my lecture. So next week, we will continue with imaging methods, okay, medical imaging methods, and also XMCD PIM in order to get the image of the magnetic domains. Then we will finish the semester. So next week, we will do the last lecture.